Wouldn't you think, in our era of modern medicine, that we would have a thorough understanding of a disease like lupus that affects millions of people around the world? We have some important clues, but honestly, much of lupus remains a medical mystery. Our knowledge about lupus comes primarily from studying mice, not humans. I'm working to change this by creating a method for studying lupus directly in human tissue. By utilizing human tonsil tissue that's removed during routine procedures or tissue from transplant donors, we've created miniature replicas of the human immune system in a dish called organoids. More on that later. By studying human tissues directly, we can unlock key insights into the biology of lupus in humans and pave the way for safer, more effective treatments for this disease. You may or may not know, but lupus is a chronic, incurable condition that most often affects young women who are otherwise healthy. For reasons we don't know, it tends to be more severe in women of color. Symptoms of lupus can vary widely from person to person because any part of the body can be subject to attack, including the brain, the kidneys, the joints, or the skin. For example, my patient, Miss B, was completely healthy until she was 24 years old, when she had her first son. Shortly thereafter, she developed debilitating joint pain, fatigue, and damage to her kidneys, which despite our treatments progressed to kidney failure. And as a result, from her mid-20s onward, she will need dialysis for the rest of her life. And unfortunately, this story of lupus is not uncommon. Lupus is an example of an autoimmune disease, and by that I mean the following. So your immune system is designed to help you fight off infections like bacteria and viruses, but it can also turn against you in autoimmune diseases. Imagine a defense network that accidentally fires at home base, creating damage to normal healthy tissue. In lupus, we know that part of what creates that damage is something called autoantibodies, circulating immune proteins that are part of a normal immune response, but can wreak havoc if they're targeted to the wrong place, like your joints or your kidneys. And currently, our treatments are blunt instruments, like steroids and chemotherapy. They globally shut down the immune system, including its ability to fight infections. So people receiving these treatments are very vulnerable to infections, and they can suffer serious side effects. There is a glaring need in this field to find a way to treat this disease and combat autoantibodies without globally shutting down the immune system. In our project, we are studying lupus directly using human tissues instead of mice. While mouse models have taught us a wealth of information about the human immune system, mice sometimes don't fully capture the complexity of human disease. In 2021, researchers developed a method for creating organoids from human tonsil tissues, which are removed and otherwise discarded after a routine tonsillectomy. Organoids can also be made from transplant tissue, including lymph nodes and spleen. So organoids are the crux of the method that I'm developing. So what are these immune organoids? Immune organoids are complex three-dimensional structures that meaningfully capture the function of the immune system. They're a representative replica of the way the immune system exists in humans, both structurally and in terms of composition. There are over 20 different types of immune cells interacting with each other in this structure. And these interactions capture key parts of human biology that are missed if you study each cell type individually at a time. With this variety of human cells interacting in three-dimensional organoids, they can produce the same autoantibodies that we see in lupus patients. And to me, that tells us that we are capturing a key part of lupus biology in patients using this new system. Organoids allow us to delve deeply into the biology of lupus in several ways. For example, we can compare organoids from normal, healthy people to organoids derived from lupus patients to understand what are the differences. We can engineer normal organoids to behave more like lupus, including producing autoantibodies with techniques, gene editing techniques like CRISPR. And we can test existing and future treatments for lupus by adding them to the organoids and studying the response to deeply understand new and existing treatments for lupus patients. Our goal is to find treatments that eliminate autoantibodies without compromising the immune system altogether. This approach isn't just limited to lupus. Personally, I've chosen lupus as a starting point because it's a disease I see in the clinic all the time, and it's a disease that I believe dearly needs more research. But this same methodology can apply to other autoimmune diseases as well, like type 1 diabetes, multiple sclerosis, and rheumatoid arthritis. In summary, by leveraging human organoids, we can address questions about lupus that have lingered for decades in a fresh and different way. In general, applying modern methods to long-standing important questions is a pathway to improving human health. Immune organoids give us a window into the complexity of human immune system, which is a step beyond what we can learn from studying mice. My ultimate goal is to create novel, targeted methods for treating lupus that treat the disease but leave the immune system more intact. In other words, safer, more effective treatments for patients like Miss B that don't put her at risk of infections. I believe this technology can pave the way for modern targeted treatments for lupus patients and fuller, healthier lives for patients with autoimmune disease more broadly.